this video we discuss one particular extension of the framework for LQ-optimal control that we developed in previous lectures, both in discrete and continuous time setting. In particular, we invite randomness into the game. We consider a standard linear time invariant state space model in the continuous time setting in this lecture. But we add a new term into our model, a term that corresponds to a disturbance acting on our system. And of course we need to specify the initial state vector, as usual. Now in this video we assume that the initial state vector and the disturbance are random. We model the randomness of the initial state vector using normal distribution with zero mean and some given covariance matrix capital sigma x. Similarly, we model randomness of the disturbance using a white noise model with spectral density SW. That is, its mean value of the mean value of the disturbance W is again 0, and the autocovariance function, which in the zero mean case is identical to the autocorrelation function, is given by SW times delta of tau. Delta of tau is a Dirac function. Well, mathematicians would immediately argue that it should not be called a function because blah blah blah, but let's skip that. Its role here is that obviously the values of the white noise at two different times are not correlated at all. The situation is perhaps less confusing in the discrete time setting where the delta function is just the Kronecker delta. That is a function that is equal to 1 for tau equal to 0 and 0 otherwise. Anyway, the distribution of values of disturbance at a given time is again normal or Gaussian if you like. The cost function. Obviously we cannot just leave it as it was in the deterministic case because both x and u are now random variables, and so would be the cost function. The straightforward way is to consider the expected value of the expression for the cost function that we used in the deterministic case. So far so good, but what if we want to consider the steady state case, that is, the final time equal to infinity? We have studied such situation in the deterministic setting and argued that it makes sense in the situations when the time of the mission is not strictly limited and the control system is expected to run indefinitely. And we have a problem here because, thanks to the random disturbance, x could never be guaranteed to decay fast enough to 0 so that the integral converges. Indeed, the integral could actually diverge in general. A solution? Scaling. We divide the integral by the length of the time interval. On top of this, we can also multiply by 2 to get rid of the classical 1/2 coefficient, just for the aesthetics reasons. The result is the mean value of the integrand. Disregarding the weighting matrices Q and R, this is what you may have already known as mean square value. The notation x at infinity and u at infinity is somehow abused here. It essentially means that the values are considered at steady state, once the transients fade out. Alright, we have a model and a cost function. How to solve the optimal stochastic control problem then? The spoiler is that the computational machinery is identical to the one used in the deterministic case. In this video and in the whole course we are not going into the details. I only want to state the result here because, let me explain, this stochastic framework only serves us in this course as a transition to some other stuff that can do similar things, but without invoking the technical results from the theory of stochastic systems and signals. And you will be exposed to that stochastic stuff quite heavily in another course, right next semester. Estimation, filtering and detection by Professor Vladimir Havlena. So let me just state the results here. First, a reasonable controller, the more so an optimal one, must necessarily be a feedback controller because of the randomness. Random disturbances can always move the system off the originally anticipated, predicted trajectory. This is quite intuitive, I guess. Second, if Gaussian white noise is assumed as a reasonable model for the disturbance, the optimal controller comes in the form of a linear state feedback, without a proof. Third, the optimal controller is independent of the initial state covariance matrix and the disturbance spectral density. This is quite surprising at first. Instead of giving a rigorous proof, let me help you develop some intuition about it. We have already seen that the LQ-optimal regulator in the deterministic case was independent of the initial state, right? Then, if we regard the initial state not only arbitrary, as we did before, but instead random, in the strict mathematical sense, with some quantitative characteristics, nothing really changes from the perspective of control design, does it? The controller just does not care. Of course, the produced control signals will depend on the particular value of the initial state and also the disturbance, but the controller coefficients themselves will be completely independent of the initial state and its possibly quantified randomness. How about the impact of the disturbance on the controller coefficients? Taking into consideration that there is no correlation between the values of the disturbance at two different times, we can view the white noise disturbance as a sequence of instantaneous resetting of the system into a new initial state. I mean, initial from now on. And since the initial state does not enter the design of the controller, neither does the quantitative description of the disturbance. Finally, but I've already mentioned it, when it comes to the actual computation of the controller gains, we can use the same solvers for Riccati equations, possibly the algebraic ones in the steady-state case. Again, no proof for this here. I've already explained that in this course we will not delve much deeper into the stochastic control issues. Still, let me mention at least this particular result. For an LQ-optimal state feedback controller, the mean value of each state variable goes to 0, obviously. But there is a formula, actually an equation, Lyapunov equation, for finding the covariance matrix for the state vector at the steady state. Enough theory, let's have a look at an example. A simple second-order state space model describing position theta and velocity theta dot of some pointing device, say tracking radar antenna. One control signal U and one external disturbance W both have a physical interpretation of torques. The disturbing torque induced by wind buffeting is modeled as Gaussian white noise with spectral density SW. The cost function considers just the steady-state behavior. One of the two state variables is actually penalized. Of the two state variables, what is actually penalized is just the position and not the velocity. Of course, the control signal does enter the cost function. A few lines of code in Matlab, should you feel like reproducing the design in Matlab by yourself. At the end, you can see the call of solver of Lyapunov equation. We call the solver to compute the quantitative description of the regulation error at the steady state, the covariance matrix for the state vector. The mean value is, of course, 0. That's what I meant a while ago when I said that the regulation error goes to 0. It goes to 0 in the stochastic sense, in the sense of its mean value. By the way, the code and even simulating model are available on the course website. You can play with it a bit. Once again, the actual control signal and consequently the state trajectories are affected by the disturbance and the initial state, but their quantitative descriptions, the parameters, were not needed while designing the optimal controller. I've already mentioned rather vaguely that this whole stochastic framework only serves us to realize some conceptual transition. Let's now start working on it. In particular, let's reformulate the problem of LQ-optimal regulation in presence of random disturbance in the following way. We consider new artificial system, the gray block in the diagram. It has two inputs, possibly vector ones, the external disturbance W and the control signal U, and two groups of outputs, again possibly vector ones, auxiliary signals Z1 and Z2 in the first group and the measured signal Y as the single member of the second group. Note that signal Y is then brought into the controller and the controller determines the signal U that is fed back to the system. Loop closed. But note that the measured signal Y is actually equal to the state vector. Thus, our feedback controller is a state feedback controller. The external input signal, the disturbance W, affects the dynamics of the system directly through the identity matrix according to the block diagram. But we can immediately substitute for the I term, the identity matrix, the BW matrix that we actually considered in the model of the system. Honestly, I failed to upgrade the block diagram. Oops. Some comment is also needed on the Z1 and Z2 signals. Obviously, these are scaled U and X signals. They are scaled through square roots of R and Q matrices. Why square roots? You must immediately see the answer if we formulate the following cost function: mean square value of Z. That is how an expression of this kind is called, right? If you now square, following the rule for squaring vectors, you immediately see that what we have here is actually our good old LQ criterion. What was my motivation for rewriting the LQR problem in this new format? I've already mentioned that we've been heading towards a new concept for characterizing performance of control systems. In particular, the concept of a norm of a system. And we start with the so-called H2 norm. But first, recall that the norm, as we use it in mathematics, is just a non-negative real number that tells us how big or small the given object is, be it a vector, a matrix, a continuous function, or even transfer function as an input-output model of a system. H2 norm is defined for a stable and strictly proper transfer function with the following formula. Recall that the star stands for a conjugate of a transfer function and TR stands for a trace of a matrix. Just in case G is a matrix of transfer functions. In the single input, single output case, the trace is redundant, of course. A super important result is that the norm can be equivalently defined in the time domain. This is due to the well-known Parseval's theorem that relates inner products in time and frequency domains. Here, lowercase g is the impulse response, corresponding to the transfer function labeled by the uppercase g. Recall that the lowercase g and the uppercase g are related through Laplace transform or Fourier transform when restricted to the imaginary axis. These two definitions of the H2 norm perhaps do not yet shed light onto why I proposed that reformulation of the LQR problem, but here is finally the explanation. H2 system norm tells us how much the system amplifies white noise input. As simple as that. In particular, the mean square value of the output vector in steady state is given by the H2 norm of the system squared times the spectral density of the input white noise, assuming that all inputs, should there be more inputs, have this same characteristic. To make this statement even simpler, assume that the white noise inputs have all unit spectral density. The H2 norm is then equal to the mean square value of the outputs. That's it. I give the result without the proof here. Either you will see the proof in the course on estimation, filtering and detection with Vladimir Havlana next semester, or you can consult the freely available textbook by Doyle, Francis and Tannenbaum. I very much recommend it, also because it's fairly slim. But now that we know that we can reformulate the LQ cost function as the H2 norm of some artificial closed-loop system, the extension from analysis to synthesis is fairly straightforward, at least when it comes to formulating the control design problem. Consider again the block diagram that we've already had here. The task for us is to find a feedback controller that guarantees stability of the closed loop in the diagram and at the same time minimizes the H2 norm of the closed loop transfer function, for which the only inputs are the components of W, and these are considered white noises. The outputs of interest are the Z1 and Z2 signals, possibly vector ones. There is an extra requirement here in that the controller is required to be just a vector or matrix of gains. A proportional controller, possibly MIMO, multiple input, multiple output. But the framework allows us to lift this constraint or perhaps introduce some other. Good news is that there are computational tools available for solving this problem. In Matlab we can use H2 syn function, but similar solvers are certainly available on other platforms. This is the end. This was the promised new paradigm for control design. pretty powerful one, capturing both deterministic and stochastic systems. It also allows us to introduce various modifications and extensions, output feedback, colored, that means non-white, noise, and many more. The full scope need not be completely obvious now, but I will try to convince you as we keep formulating control problems in this new framework. In the next video, we will break the assumption upon which we have been relying so far, namely, the assumption that all state variables were measured.